So let's start. So the last time we started a new topic of zeta functions, and we started in a big generality containing the classical Riemann zeta function, but then we specialized to the case of a variety over some finite field, and I do not explain what I mean by this, but well, it depends on your background. Say maybe it's an affine variety given by some equations with coefficients in this ground field in the affine space, or maybe it's a projective variety given by some homogeneous equation in projective space, or maybe it is a scheme glued from affine spaces. Just in fact, from starting from today, we will study just hypersurfaces in affine spaces, just one equation. So whatever you prefer, the simplest possible case. And now to this we associate the zeta function of x naught and counting variable t. So this is defined as the product over all closed points of some binomials. Like this, Euler product. And well, maybe. So the closed point means that, well, in case it's an affine variety, there is a corresponding ring of functions, and then it corresponds to a maximal ideal, and the closed model of this maximal ideal is a finite field, and this finite field is an extension of the ground field Fq, and the degree of this extension is this degx. Okay, and now what do we proved last time? We proved that we may consider for any r the extension of our ground field Fq to the r, and then we can consider the points of x, which is the scalar extensions from x0. This. Okay, and the number of such points is denoted by nr, and they are those guys here who have degree r or some divisor of r. Okay, so whose residue field is a subfield of Q to the r. And now this nr is the sum over all x in the closed points, whose degree divides r, and you just sum up the degrees of x. Okay, and also it is useful to view x naught as the set of orbits Frobenius. By Frobenius, I mean x goes to x to the power q. So it's Frobenius with respect to this ground field. So these are just Frobenius orbits in the closed points of x. Okay, so we discussed all this last time, so maybe I will not repeat the discussion. But what I promised to do last time is to develop some tricks due to André Weil, going back to 1949, a very famous paper of his, where he formulated so-called Weil conjectures. They were among the most important moments in the last century. So somehow they determined the progress of mathematics for the next half a century. Well, there were some other things like this, but this among maybe five most important well, developments in mathematics of last century. Okay, so his idea was like this. Well, we are counting F, Q, R points over X naught, and they are the same as fixed points of this power of Frobenius in X. Okay, so we are going, pardon me? Yes. Okay. Thank you. So there are fixed points in X. Now X is an algebraic variety over algebraically closed field. So we may apply some generic intuition to it, even though it is in characteristic P as opposed to complex algebraic varieties where we can apply some topological intuition. But still, let's try. So there is the Lefschetz fixed point formula. And it says that the number of fixed points of Frobenius is equal to the alternating sum of traces of this Frobenius endomorphism on the cohomology of our variety, well, with some coefficients. Now, first of all, if our variety is, say, affine, then it's important that the cohomology is taken with compact support. Okay, compactly support cohomology, and then usually you can take cohomology with, say, rational coefficients or real coefficients or whatever. But so at the time of 1949, it was not clear at all, and probably they wanted to have here rational coefficients. But then, as Alexander Grothendieck did develop the required theory 15 years later, it turned out that it's absolutely impossible to have cohomology with rational coefficients for some not very complicated reasons. There is no such thing as they dreamed. You must have chosen some auxiliary p-adic field. So this L must be not P. But you must make a choice like this. And such theory does exist. Okay, but maybe we shouldn't worry about this because it's all just wishful thinking. But I say that 15 years later, Grothendieck proved that this does work like this. Maybe if you encountered Lefschetz fixed point formula, maybe remember that it doesn't just count the fixed points. It counts the fixed points with signs or with multiplicities, certain multiplicities. And here, all the multiplicities are just one. So it does really count the number of fixed points. And why is this? Because in the Lefschetz fixed point formula, the multiplicities are the intersections of the diagonal inside x times x and the graph of your automorphism or endomorphism. So they're local intersection multiplicities of the graph and diagonal. But in our case, Frobenius, well, in some sense, it's an automorphism, but in some other sense, quite the opposite. For example, its differential is identically 0, right? Because it takes x to the power q, and its differential in characteristic p is just 0. So it means that whenever it intersects diagonal, it looks like this. Well, I don't know how to draw this. I don't know. But it's always horizontal at the, well, I don't know. I don't know what to do. It doesn't look like graph. But anyway, I want to stress that it's always horizontal at the points of intersection with diagonal. Okay, so all the intersection multiplicities are just 1. So we really do count just points without any plus minus 1 multiplicities. Okay, we have this formula. And now let us rewrite it once again. X to the power Frobenius to the r is the same as the number of points of x naught with coefficients in f q to the power r, and is the sum, the alternating sum of traces of Frobenius to the power r. Well, I don't know. It's the induced endomorphism of cohomology. This star means the induced by Frobenius endomorphism of cohomology with coefficients compactly in ith compactly supported cohomology of x with coefficients in QL. Okay, fine. And now let's take the logarithmic derivative of our definition of the zeta function there. And what do we get? We get t capital over dt logarithm zeta of xt is the t d over dt zeta function divided by the same zeta function. Okay, so this is what the sum over all closed points minus negative degree of x times t to the power degree of x over 1 minus t to the power degree of x. So this is the sum over all closed points, the sum over positive k degree of x, t to the power k times degree of x, yeah, just geometric progression summation. And finally, this is equal to the sum over all r, points of over fq to the r times t to the r. Okay, and maybe let's number this as 1, this as 2. Then I will need the third formula, namely that for any endomorphism, say f of any vector space, but finite-dimensional vector space V, if you take the logarithmic derivative of the sort of characteristic polynomial determinant of 1 minus ft on the space V inverse, then you get the sum of traces of f to the power n to the power r, the generating function. And this will be our third ingredient. So let's prove this. This is something elementary, and for a change can be proved. So let's prove this. Maybe in some simplest example. What could be ft? No. Well, maybe this one, meaning the identity of V. So it's like characteristic polynomial. This is some formal variable. It's like it's almost characteristic polynomial. Yeah, you take this endomorphism. Yeah, this. I mean, well, how to? This is an endomorphism of V. So I don't know how to write it better. The same thing here. It's an endomorphism of V. So it's another comma. Maybe I should put this V into the subscript of determinant. I don't know. But anyway, so what is the simplest example? No. It's definitely wrong. This is not the simplest example. I know. Right. Yes. One-dimensional. It's also diagonal, but so let's be one-dimensional. Then f is just a scalar. And what is written here? Ft inverse. Yes. Yes. Yes, and how is it checked, this polynomial equation? I think I already used it. Yes, absolutely. It's just summation of geometric progression. So yeah. Okay, so yeah, so there are two very scientific approaches. One, as Peter explains, let's assume that our field is complex numbers. Okay, and then as Michael explains, if you know it for one-dimensional case, you know it for diagonalizable case, just direct sum of one-dimensional cases. And on the over complex numbers, the diagonalizable operators are dense, and those functions are continuous. So if they coincide on the dense set of diagonalizable operators, they coincide everywhere. So we proved it over complex numbers. Absolutely, yes. So in fact, it's some identity just for matrix elements of your operator f, and it is over integers. So if you prove it over complex numbers, it works over integers, and then we can specialize to arbitrary field at all. Okay, so some dirty logical trick, so to say, but it works. And another scientific approach is via, so to say, Grothendieck K-theory. So you note that, well, first of all, as Michael said, if you know it for one-dimensional, you know it for diagonalizable because it's direct sum. But even better than this, if you know it for extension, so if you know for F1, F2, and then something here, then it's still fine, because both determinant and trace, they care not about this. Yeah. So it's true in exact sequences. If you know it for sub and quotient, then it's true for the middle term. And then any operator can be, well, can be made upper triangular. Okay, so there we are. It's proved. Now we have these three basic constituents, and now just we plug one into two, and apply three, and we get that the logarithmic derivative of the zeta function equals the alternating sum of logarithmic derivatives of the determinant of 1 minus Frobenius to the power r times t in ith compactly supported cohomology of x with coefficients in QL inverse. And now we just take logarithmic integrals and we arrive at the Andreev formula that the zeta function is the alternating product of characteristic polynomials of Frobenius endomorphism on the compactly supported cohomology, like this. Okay, so this is the fantastic conclusion. So in particular, it's rational function of t. Okay, and the numerator corresponds to odd cohomology. The denominator corresponds to even cohomology. And the degrees of these polynomials are the dimensions of cohomology. And now there is one extra piece of information. This is the Riemann conjecture, which says that there are no cancellations. So in principle, there might be cancellations between even and odd dimensional cohomology characteristic polynomials, but this never happens. So it says that if x naught is a smooth projective, then for any I, the polynomial maybe now I modify it slightly. So I take, well, I divide by t and take t inverse. Is and then since x is projective, there is no difference between compactly support cohomology and usual cohomology. So I don't write compactly support anymore. Okay, so this is a polynomial in T. And the first thing is that it has integral coefficients. So we used this strange auxiliary choice of p-adic coefficients, but the outcome does not depend on this L. It's independent of L. Okay, and all the roots of this polynomial in complex numbers. So we are doing something absolutely crazy. Yeah, first we introduced some p-adic field. Then we said that polynomial actually has integral coefficients, and then we solve it in complex numbers instead of p-adic. The roots in C all have absolute value q to the power I over 2. Okay, so if we worked with this thing, we would have q to the inverse, negative I over 2. In particular, there could be no cancellations. So each cohomology remembers its number just by the absolute values here. And in fact, such roots are called Andreev numbers. Yeah, but by definition, they're algebraic numbers, all of whose conjugates by Galois group have the same absolute value. Yeah, for example, if you take like 1 minus square root of 2, it's nothing like this. Its conjugate will be 1 plus square root of 2 and will have different absolute value. But those are very special algebraic numbers, and only they occur. Okay, and just a small survey: who didn't know this? Who did hear about this before? Who did hear about this before? Very good. Yeah, but well, not many people understand this. It looks very mysterious, but I remember when I have heard about this for the first time in my life. It was November 29th, 1985. And so I was absolutely struck by this. And somehow it determined all my life course, mathematical life course, when I heard this. I find this absolutely striking. So this was also this conjecture was also proved. It was proved in this framework developed by Grothendieck, but it was proved by Pierre Deligne already after Grothendieck quit mathematics in 1973. Okay. I mean, this part, Riemann-Weil conjecture, this rationality part was proved by Grothendieck himself. But maybe around the same time, this rationality so at about 1965, so it was proved by Grothendieck. And independently, by some different method, by Dwork. And we're going to discuss the proof due to Dwork. The proof of Grothendieck is just this. So he very straightforwardly and simply-mindedly developed this theory of cohomology and proved the Lefschetz fixed point formula. This was it. But this, well, it took like about 1,000 pages and development of all algebraic geometry in order to be able to talk about cohomology of algebraic varieties in characteristic P. And the work had some different p-adic political approach that we will follow. And maybe I should mention that apart from this rationality and Riemann way, there is also second functional equation. And then it also immediately follows from the Poincaré duality. So it was also developed by Grothendieck, and this was accomplished by Deligne. So it's much harder somehow. After you develop the foundations of p-adic cohomology, then you need to do an immense work to prove the Riemann-Weil conjecture. So it's absolutely out of our reach, but we will prove the rationality, hopefully. Okay, so let's start moving towards this rationality. Analytic argument. And yes. Well, it will be in your home assignment, the next home assignment. It's a very simple reduction of general, say, projective or affine case to affine hypersurface. It's very elementary and easy. So we will concentrate on this case. But first, let's do some foundations. So maybe let's start with an elementary example, which will be not affine, but will be x is just projective line. Okay, so then what do we know? We know that the number of points n r is q to the power r plus 1. Yeah. And also last time we proved that the zeta function had another presentation, the exponential of the sum from r equals 1 to infinity of nr t to the power r over r. It was proved last time. And so let's apply this. What do we get? The exponential of the sum of q to the power r, t to the power r over r plus t to the power r over r. Okay, and this is, the exponential of negative logarithm of 1 minus qt minus logarithm of 1 minus t. And so this will be 1 over 1 minus t, 1 minus qt. So it's just what I said before, right? Because for P1, the zeroth cohomology of P1 is one-dimensional. There is no first cohomology in numerator, and the second cohomology is also one-dimensional. All right, so in this very simplest example, it does work. Okay, so we'll need the following lemma. Assume this that our variety is affine, and it lies in n-dimensional affine space, and then I claim that under these circumstances, the coefficient of t to the power j in our zeta function is this coefficient is at most q to the power n. N is the dimension of ambient space, j is the power of t, and the proof is an immediate corollary of this, because you see that those nr's, nr of x naught is at most nr of the affine space, which is q to the power nr. Okay, but from this formula, because the exponential series has positive coefficients, again there are no cancellations, write that coefficient twice. The zeta function of x naught is smaller than the zeta function of the affine space, and for this it's clear. So we are done, and now in the next home assignment if you know the rationality of the zeta function for affine hypersurfaces, then you know it for any affine or projective variety, just by some excision procedure, or how is it called, inclusion, exclusion, whatever. And so the key result is this, due to work. If x naught is the set of x in an such that f of x is 0, so the hypersurface cut out by a single equation. Then the zeta function of x naught is the ratio of two polynomials, well, maybe p of t over q of t, with constant terms 1. Okay, so hopefully we will prove this by the end of this year. This will be our last topic. And now we start some preparations. For example, maybe you remember at some point, maybe a month ago, we had some Dwork lemma. about integrality of coefficients of power series, it will be very instrumental already today. And the very rough idea must be appealing to Peter, because it's very much in the spirit of Alexander Kalmynin. We'll just apply analytic number theory, so to say. So we consider the counting function. Say C. So this function is from FQ to just the integers, even positive integers, namely, say C of Z equals the number of points in the affine space Y in the affine space, such that f, this equation f of Y is equal to Z. Okay, so in particular, an R or maybe I should say fq to the power R. Sorry, to the power R. Yes, like this. So an R is just C of 0, the counting function at 0. Okay, and now let's consider an auxiliary function, namely, we set S of x0 equals the sum over all points in the affine space of exponential of 2 pi I over p, the trace of x naught times f of x. And by trace, I mean a trace from f q to the power r to fp. Okay. Okay, so x naught lies fq to the power r. So we apply our equation function. We obtain some element of fq to the power r. We multiply it by a certain x naught. It is an element of fq to the power r. Then we take the trace of this field extension. We obtain the prime field fp. And this makes sense, and it lies in complex numbers. Okay, so this is a function once again from S is a function from f q to the power r to complex numbers. Yeah, and this is nothing but the Fourier transform T is counting function. Shall I say a few words about Fourier transform, or is it known to everybody? Any reaction? Yes, just functions of well, C of f q to the r to itself. So I don't get it. Oh, now I will have a clear answer. Shall I go over Fourier transform for finite groups, or is it well known to everybody? It is well known to everybody. Good. Pardon me? Abelian finite groups. Pardon me? Great. So we're using this Fourier transform. Fine. And it implies that the value of the counting function at 0 is by the way, if everybody knows about the Fourier transform, then tell me what is this in terms of Fourier transform. So S is the Fourier transform of C. So if I want to calculate my counting function at 0 in terms of S, what should I do? Right. Yes. Yes. So it's the integral over fq of S of x, so to say. But when I say integral, I must specify some measure, and I guess it's 1 over q, most probably. But then okay. So this is how we will count the number of points, just by this Fourier transform. But we will perform this Fourier transform not over complex numbers, but over the Tate field. Okay, and so we will start this. We'll start this business right now, and you will see that already the very beginning is absolutely non-clear. So if we try to define this, it will take us all the remaining time today, just for definition of this. Okay. So we'll study the characters group homomorphisms. Say from an abelian group to the multiplicative group of the Tate field. And we fix an pth root of unity in the Tate field. And then if I have a number in Fp, or maybe Fq, or even Fq to the R, or even S, then it goes to Fp, and then I well, take an element in here, and then I take epsilon goes to epsilon to the power trace of A. So it'll be a character from f q to the power s to the Tate field. Okay, and we will construct but an analytic function theta unfortunately it will have nothing to do with the usual theta functions, elliptic functions. But it will have the property that theta of t times theta of t to the power p times so on times theta. Yes. Epsilon to the power trace of A. So trace of A lives in the prime field Fp, and the epsilon is pth root of unity, so this is well defined. Maybe, okay, so maybe A goes here, yeah. Yes. Right? So this is a character, yes, from this finite field to the multiplicative group of the Tate field. Okay, and we want to well, write down this character as the product of certain theta functions. So for for t equals the Teichmuller representative of A. So that's our goal for today. And now we'll consider an ramified extension of QP of degree S. So the residue field is extended, but nothing else. And then the trace in this sense from K to QP of the Teichmuller representative of A. So the trace of A is just the sum of powers of A plus A to the power of P plus so on plus A to the power P to the S minus 1. Right, because I just have to add up all the conjugates, and the conjugates over finite field are just these powers, the images of Frobenius, but the Teichmuller representatives are multiplicative, so I get this. And in particular, this is a p-adic integer. Yes. Yes. Right. From K to QP, we want to get a p-adic number. well, if our original A were in the prime field Fp, then its Teichmüller representative is in Qp and even in Zp. But if A is an extension, then its Teichmüller representative also lies in this unramified field. But this unramified field, or rather its ring of integers, is the Witt vectors of this field. Yes. So your question is about how to compute traces, right? Frobenius companion form of matrix. Yeah, that's one approach to compute traces. But there's another one, just the sum of all Galois conjugates. And here it is written. Yes. Okay, so we can compute this. And also this trace of the Teichmüller representative from K to Qp is the same as the trace of A itself, modulo P, and hence epsilon to the power trace of A is the same as epsilon to the power trace of the Teichmüller representative. Okay, and now we set lambda is epsilon minus 1, and then the order of lambda is 1 over p minus 1. Let's and now let's recall why this is so. I forgot, maybe you had this in home assignment, maybe not, I forgot. But let's recall anyway. Why is it so? Yes, p sort of unity. So again, there are various, yeah, that's a very best solution, yes. Because a lazy bone should say that this is a totally ramified extension of degree p, and so I mean, if you attach this to QP, if you extend QP with p sort of unity, this will be a totally ramified extension, and this lambda will be a uniformizer. So this, but Michael suggests a better explicit approach. So what do you say once again? So our well, epsilon was the root of x to the power p minus 1. Yeah, and the lambda is epsilon minus 1, so it's a root of what? Root of, well, x plus 1 to the power p minus 1. Yeah, but which polynomial? Eisenstein, yeah, very good. Eisenstein polynomial. So this lambda is necessarily the uniformizer and has exactly this order. Okay. So we want to compute 1 plus lambda to the power Teichmuller representative A plus Teichmuller representative A to the P plus so on, plus Teichmuller representative to the power P plus minus 1. And naively, we could take g of t is 1 plus lambda to the power t. So just by the Newton binomial formula, the sum from 0 to infinity, t minus 1, so on, p minus I plus 1 over I factorial, and then our function like this, theta, naively, we want to this g. So this would be equal to g of t to the power p, g of t to the power p plus minus 1. Okay, but unfortunately, if our A is not in the prime field Fp, is not in Fp, then, as we discussed already, the corresponding Teichmuller representative is not in Zp, but in its extension. But then it means that the absolute value of the difference A minus I is 1. Right? I mean, they're both integers and there are no cancellations, so it's just 1. And hence, it implies that the order of A times A minus 1 times so on, A minus I plus 1 is and also, sorry, lambda to the power I and over I factorial is I times order of lambda minus I minus Si over p minus 1. So it was your first home assignment or second home assignment, how to compute the order of I factorial. This is the sum of p-adic digits of I. Yeah? Okay, and so because we know the order of lambda, it cancels out and you get just Si over p minus 1, and it does not go to infinity. So this series diverges. Okay, so this naive approach does not work, unfortunately. And the better approach will be as follows. We consider the following function, auxiliary function f of xy in two variables. It will be 1 plus y to the power x, and then times 1 plus y to the p to the power x to the p minus x over p times, well, so on. Well, maybe 1 plus y to p squared times to the power x p squared minus x to the p over p squared, and so on. And this will be some power series with rational coefficients. And now we'll establish some properties of this f function. So first of all, I have to explain what I mean by taking those x powers of 1 plus y. So these are just given by Newton binomial formula. And in this sense, I will obtain the power series into variables. So f of x, y will be the product of b x p of y. So about a month ago, we discussed this binomial, Newton binomial function. P is just means that the coefficients are in CP or whatever, in QP. Okay, so this is like the exponential, and this is 1 plus y. So it is this times b x to the p minus x over p over y to the p, and so on. And this is equal to the to the sum of x times x minus y minus I, sorry, and so on, x minus x minus 1, x minus I plus 1 over I factorial times y to the power I, and then times the product over n and here x to the power p to the n minus x to the power p to n minus 1 over p to the n, and then x to the power p to the n minus sorry, pp to the n minus x to the p n minus 1 over p to the n minus 1, and so on, x to the power p to the n minus x to the p n minus 1 over p to the n minus I plus 1, and then y to the power I, p to the power n over I factorial. Yeah. Okay, so this is just the definition of binomial functions, and so we get a function of two variables. So it starts with 1, and the first coefficient in x is also 1. And in y as well. And now we will use this Dwork lemma to prove that the coefficients are actually p-adic integers. So what do we have to check? We must check that when we substitute the pth power of x and y and divide this by the pth power of our function, then we get something which starts with 1 and then is divisible by p. You have to check this. Yes. But yeah, you can yeah, for example, by induction, yeah, or just the same way. And how do you remember we proved it? How do you remember how we proved it? I have such good lecture notes. Okay. So f of x to the p, y to the p over the pth power of f by definition is 1 plus y to the p to the power x to the p, 1 plus y to the p squared to the power x to the p squared minus x to the p over p, and so on, over 1 plus y to the power px, 1 plus y to the p to the power x to the p minus x. Yeah, just to take the pth power, well, like here, and so on. And so everything cancels out, and you just are left with 1 plus y to the p to the power x over 1 plus y to the power px. Okay. And we won't have to check that this is of this sort. So now let's apply the Dwork lemma to the power series 1 plus y very simple-minded series. And then we get that 1 plus y to the power p over 1 plus y everything to the power p is 1 plus p times certain function g of y for some g of y with integral coefficients. Yes, so Dwork-Lemma worked in both directions. Yeah? So we apply the converse direction, and hence, pardon me? What is Dwork-Lemma? The Dwork-Lemma says that well, maybe we formulate it for one variable, but it is the same for any number of variables. So if we have to find out that certain function has integral coefficients, then it's equivalent to the fact that when you divide f of variable to the p over f to the p, then this has the constant term 1, and then all the other coefficients are integral and divisible by p. That's the Dwork-Lemma, which we proved some month ago, in October, anyway. Okay, so where are we? We know that there is some function with integral coefficients, g, and hence 1 plus y to the p to the x over 1 plus y to the power px is 1 plus p y g of y to the power x, and this is equal to the sum over all positive integers, x minus 1, and so on, x minus I plus 1 over I factorial, and has coefficients in divisible by p. Sorry, where? Oh, I forgot. I forgot. Here, sorry, I forgot the main term. P to the I, g of y to the I, y to the I over I factorial. Sorry, and then this lies in 1 plus p x zp of x and y plus py okay, and finally this implies that our function f does have integral coefficients. Okay. Okay, so now I have to stop here, but next time from this function we will produce our desired theta function, and this f will have, well, it will give rise to much better convergence. So the naive approach failed because we obtained the divergence series, but using this auxiliary f function we'll be able to construct a solution of our problem convergent on the whole unit disk, and even better. Okay, thank you.